Hello everyone and welcome to today's Geobites presentation on global human impacts and the Anthropocene. My name is Stacey and I'm one of the Schools and Colleges Liaison Assistants at the University, and today I'm joined by Dr. Graham Wilson, who'll be running today's Geobites presentation. Would you like to say hello, Graham?
Hello everyone.
And you'll get to see Graham shortly. We're also joined by Isabel, who will be moderating any questions as they come in. Would you like to say hello, Isabel?
Hi there everyone.
Brilliant. So I'll shortly be handing over to Dr. Graham Wilson for the presentation, but just a few things to note before we start. During the presentation, you'll be given the opportunity to ask questions and get involved in activities via the chat function on the right-hand side of the screen. Your audio and video won't be shared, but any questions, comments or answers that you do post can be done so anonymously if you wish. Just need to make sure that you click you wish to be anonymous before posting the question or comment. You can like other questions that people may have asked just to indicate your interest also. Isabel will collate any questions and ask Graham these at the end of the session. Okay, so I think we're ready to start. Over to you, Graham.
Thank you, Stacey. Hopefully everyone can hear me loud and clear. Well, thank you for joining me today for this talk. My name is Graham Wilson. I'm a lecturer in physical geography at the University of Chester. And today we're going to be talking about global human impacts and the Anthropocene. Now, what I'm trying to do today, just trying to move my slides on. There we go. So the purpose of this talk really is to take a longer term perspective of human impacts. Now, the way we do this at Chester, we do a third year module in this. And we use the recognition of the Anthropocene epoch as a vehicle to study long-term impacts and the legacy of human activity, to try and demonstrate that human activity is nothing recent, just recent. It's got a much longer history. So what do we mean by the Anthropocene? Because this is something you might not have heard of before. Well, this as a term was first proposed in the year 2000 in a publication, and it was proposed as a term that should be used to recognise our current geological unit of time. Okay, so it's in other words, it should have a formal definition as a unit of time in our geological timescale. And it's derived from anthropos, human being, and kainos, new. There is a history to this. You know, this is reared its head in various forms over the last 100 or 150 years, but this is the most recent time that it's been proposed to recognise our current epoch, if you like. Now, the proposition is based around the fact that humans have had a global impact over the last sort of 200 years or so, and the term is basically there to characterise the central role that humans have had on all parts of the world, on all different systems, on climate and so on. So it's really to emphasise the central role of humans in environmental change. So why was it presented? What was the thinking behind this? Well, this is just a snapshot of different impacts that humans have had, and I won't go through all these in detail. It's just to sort of illustrate a point. So, for example, you can take any one of these at random. Paper consumption in tons, in million tons here. Loss of tropical rainforest and woodland increasing. Transport, number of motor vehicles increasing. Population now standing around 7 million or so. 7 billion is increasing. Urban population increasing. Flooding increasing. Water use. Species extinction. So the commonality here is that everything is going in the same direction, in a sort of bad direction in terms of rapid and increasing impacts on all different aspects of the Earth by humans. And so this drove the authors, Crutzen and Stomer, to argue that we should really recognise that we've entered a new geological time period, one in which changes, global changes, are driven by humans rather than natural variability. So possibly the most sort of famous example of this is fossil fuel combustion, and obviously this is very topical in terms of Glasgow, but also very topical over the last few decades. And this is because in a few generations we've managed to exhaust most of the fossil fuels that were generated over hundreds of millions of years. And these greenhouse gases obviously have an impact on climate and cause the climate to warm. But what is the significance of this? And to talk about significance, you have to take a step back and take a longer term perspective. So here are ice core records of greenhouse gases, both methane, which is CH4, and carbon dioxide, CO2. And basically when ice is formed, so we're talking about the Antarctic ice sheet here, when surface ice is formed, it traps bubbles of air. And in that air is carbon dioxide and methane. And these fossilized bubbles form part of the ice. And so you can drill through the ice, melt the ice, and then measure the amount of CO2 and methane that's contained in that ice package. By drilling down through the Antarctic ice sheet several kilometers, you can reconstruct atmospheric greenhouse gases, and this is what this diagram is. So this now extends to 800,000 years. This is a slightly dated diagram, but it serves our purpose. And so what you can see is carbon dioxide levels oscillate. Okay, there's a distinctive pattern to this, a sawtooth pattern, which we won't go into, but it basically oscillates between high concentrations during interglacials and low concentrations during glacials. Okay, high concentrations, low, high, and then low. And then we've deviated from this pattern recently. Okay, so we expect high concentrations because we are in a current warm period. But what we're seeing now is that CO2 is just increasing and increasing. I checked today, we're at 412 parts per million. And 1,892 parts per billion for methane, and this far exceeds anything seen in the ice core record over the last 800,000 years. And so it's extremely unusual and something that you don't expect to happen as part of a natural climate cycle. This also has other effects because carbon dioxide is absorbed by the oceans and it causes the oceans to become more acidic. And so there's all sorts of different problems with this, and it's also offset or delayed the next glaciation. So to think about the recognizing a new geological period of time, we have to sort of step back and think about how we divide geological time briefly. And geological time is divided into a series of hierarchical units. So we start with eras, big changes. Then the era is subdivided into periods, which are slightly smaller global changes, and periods are subdivided into epochs. Okay, so at the minute we are in the Cenozoic era, which began 66 million years ago. And within that era, we are in the Quaternary period, which began 2.6 million years ago. And this marks the start of the ice ages, if you like. And then the Quaternary period is in turn subdivided into the Holocene, which is our current geological epoch, and the Pleistocene, which began 2.6 million years ago and ended 11,500 years ago. And so these divisions represent changes in the functioning of the Earth system. So maybe we've got some large scale extinction events which mark a boundary, or you have a major change in climate. So for example, the start of the Cenozoic is marked by the iridium peak. Now iridium is a chemical which is quite rare on Earth, but is common in meteorites. And so this leads to the Orbis Hypothesis, in which meteorites struck the Earth 66 million years ago and contributed to the demise of non-avian dinosaurs. So we had a mass extinction event. So that's an example of how a geological time period is defined in the geological record. So what would an Anthropocene epoch look like? Well, this is one example. This is how it might look. So instead of the Quaternary being subdivided into the Holocene and the Pleistocene, maybe the Holocene or current epoch has finished, and instead we see the Anthropocene as our newest geological time period. So the question is, have we entered a new geological epoch? Now, despite what you might think if you've heard of this term, and it's bounded about quite a lot, it's not formally ratified as such. It's still in discussion, and so this discussion is led by the Anthropocene Working Group, and they are charged on behalf of the International Commission on Stratigraphy to go away and think about, well, should we really recognise this as a new time period and put their proposals forward. So in terms of how this all works, over the last few years, they've gone away as a group. They've decided as a group that we should recognise this as a new geological time period, and there's a link there to the BBC article about that. They take this to the International Commission on Stratigraphy, and they have to do a supermajority vote in favour before it can get ratified by the International Union of Geological Sciences, which looks after the geological timescale. So we're a few steps away from that. Now, this is where it gets controversial, because not everyone agrees that we should be recognising a new Anthropocene epoch. So that's the first controversy. The second one is, well, if we are going to recognise it, when did it start? We need to agree a start date. And again, this is debated quite ferociously in the academic research, and we can say it boils down to sort of four potential candidate events. So we can recognise the start of the Anthropocene by something known as the Great Acceleration, or maybe the Industrial Revolution, or maybe the early anthropogenic hypothesis, or maybe the Orbis Hypothesis. So what we're going to do in the next few slides is just explore these four events, and particularly these last two, to demonstrate the scale and the history of human impact on the Earth. So we'll start with the most recent, the Great Acceleration. Now, this is the candidate event that is most favoured by the working group to recognise the start of this new geological time period that we may be in. And this is associated with rapid changes in all sorts of things across the Earth. So things like plastics started to flood the environment, and we know we've got a problem with plastics and microplastics. Fertilizers were used and were widespread, and that's led to pollution and issues with biodiversity. Concrete is used. That's got a massive carbon footprint, but is also an artificial substrate, which there's enough concrete on Earth that you sort of pave the entire Earth by about 1 centimetre. Leaded petrol is used, again, chemicals associated with that. All sorts of different things are increasing. But then we've also got the first atomic bomb. And the atomic bomb blast in 1945 left enough long-lived uranium and plutonium as byproducts to mark in the sediment record the start of this new geological epoch. So that's favoured by the working group. Okay, so we can just see an example of that, and it's called the Great Acceleration because you can see around about sort of 1940 onwards, the pace of a lot of these different impacts really picked up. So you've got an inflection point around about sort of early 1900s, and the pace really picked up. So that's the idea behind the Great Acceleration. One that might be familiar to you is the Industrial Revolution. This was proposed to recognise the start of the Anthropocene by Crutzen and Stomer in the original paper, because they argued that the scale of human activity was the most visible over the last 2 centuries since the start of the Industrial Revolution. And we also see the first notable increase in atmospheric CO2 and methane above previous longer term values. Okay, I don't think that is quite correct to say that, as you'll see in the next few slides, but certainly you started to see quite a rapid rise in these gases. Now, the problem with the Industrial Revolution is it's time transgressive, so it's not a impact event in terms of it happened at the same time everywhere, because different countries underwent the Industrial Revolution at different time periods. So it's not a neat single event that can be used to mark the start of a new geological epoch. So let's go a little bit further back in time, and just for you to recognise the profound impacts that humans have had over thousands of years, not just since the Industrial Revolution. So implicit in the view of taking the Industrial Revolution as the start of our new geological epoch is that human activity before the 1800s was pretty small, and that just isn't the case. So we can take the early anthropogenic hypothesis. So this is one of our 4 candidate events, and this is something that relates to early human activity. So it relates to CO2 release by early humans and methane release. CO2 from deforestation and methane from wetland generation. So let's just go through some examples of this. Now, we can actually say that carbon dioxide started to rise around about 7,000 years ago. Okay, it's not associated just with the Industrial Revolution. So greenhouse gases were being emitted by early humans from 7,000 years ago. And this is because of deforestation. And what we can see in this slide is the centre of farming. Okay, farming originated in different areas of the planet almost simultaneously. There's some slight differences, but crops were first domesticated, or plants were first domesticated in the Near East here around about 9,000 years ago, and then this technology spread throughout Northern Europe, and so we started to domesticate plants around about 6,000 years ago, and we use that to sort of grow food. Now, obviously, to grow food on any scale, you need to clear forests. And so there was widespread deforestation to make way for this. And when you clear trees, you release carbon dioxide. Okay, so this widespread or spread of technology to remove forests to grow food resulted in carbon dioxide being released. Now, I showed you an earlier slide where we had carbon dioxide increasing and decreasing in a pattern over the last 400,000 years. So it is quite predictable. But what's happened over the last several thousand years is carbon dioxide has sort of gone down slightly, which is what you'd expect as part of a climate cycle. But then it's changed its mind and it started to increase. So atmospheric carbon dioxide started to increase around about 7,000 years ago. Okay, so this is not just the modern Industrial Revolution. Greenhouse gases were being emitted through deforestation around about 7,000 years ago. Now, what we've got in blue, this is the previous activity of carbon dioxide over multiple climate cycles. And in this stage of an interglacial, carbon dioxide always goes down, it never goes up. And so this increase in CO2 over the last 5,000–6,000 years is odd. Okay, and this points to a human presence and human impacts. Okay, so the other one is methane. This is another greenhouse gas. And again, it's related to early human activity and food production. And what we see is a spread of farming again, but in this case, we are growing rice. Okay, so this is the center of rice growth, and to grow rice, you need wet conditions. So they were artificially creating wetlands and flooding areas to grow rice. Now, wetlands create methane as a byproduct, and therefore methane began to increase in the atmosphere from around about 5,000 years ago, and it's steadily increased. Okay, so you can sort of see that there. and it's related to the spread of rice cultivation, which started around about 5,000 years ago in China. Again, a similar graph here. So we've got ice core records of atmospheric methane, and you can see that the methane started to decrease in the early part of our interglacial, and then it's changed its mind and it started to increase again 5,000 years ago. So this is due to rice cultivation by early humans. And again, in this part of our interglacial, as in previous interglacials, methane should be decreasing. It shouldn't be increasing. And so again, this is odd, and it's a departure from the last several glacial interglacial cycles. So why does this matter? Well, it matters because they could have offset the next glaciation. So what we see here is we've got an increase in temperature from the last glacial to the start of our current interglacial. And without this human activity, we would expect climate to cool from around about 6,000 years ago, okay, to the present day and into the future. That's the normal pattern of an interglacial cycle. But instead, early humans have released methane and carbon dioxide. They've offset this cooling and caused the Earth to be slightly warmer than it would otherwise be at this point in time. And therefore, they have offset potentially the next glaciation, which should have started, according to Ruderman, around about 1,000 years ago or 2,000 years ago. So this is one proposition to recognise the start of our current geological epoch. And the proposed date is 5,000 years ago to mark the clear rise in atmospheric methane, which characterises a global human impact in terms of the discovery of food production, which allowed civilizations to develop, and we've got modification of the global climate, and therefore this arguably is the first large human impact, global human impact. Now, just to introduce the sort of final candidate event, this is known as the Orbis Hypothesis. And Orbis is the Latin name for world. Now, this hypothesis has a candidate start date slightly later than the early anthropogenic hypothesis, and it's linked to the generation of the first global trade networks, which link the old world, or Europe, China, and Africa, with the new world, the North and South states. So we've got USA in the north and South America. Now, this happened post 1492. Okay, so this is when the Americas were so-called discovered. So the sort of Caribbean was discovered by Columbus, and after that discovery and the annexation of the Americas, we had trade. So New World and Old World crops were traded, so between the Eastern and the Western hemispheres. So post 1492, for the first time in terms of trade, the two hemispheres were connected and trade became global. And this is the start of the modern world system, according to social scientists. And so this marked the beginning of the world that we now know, I guess, because we've got these exchanges in foodstuff permanently altered and dramatically altered the diet of almost all of humanity. So the reason for this is because we exchange different crops. So potatoes are from the Andes. That's a New World crop, and it's currently the fourth largest food crop in the world. And obviously, you know, we eat chips and potatoes. Corn was first domesticated in Mexico, and obviously that is familiar to us. Cassava is a South American crop, but all of these were subsequently grown across Europe, Asia, and Africa. Going the other way is Old World crops now planted in the New World, so sugarcane from South Asia and wheat from the Eastern Mediterranean. And as well as plants, we had domesticated animals moving so things like cows and pigs and goats and horses. And accidental transfers as well, such as species of earthworms. And so what we can see is this is a very big magnitude event, because we've got a swift and ongoing radical reorganization of life on Earth without geological precedent. This is from a publication in 2015. We know that this altered the diet of almost all of humanity, and so this set in motion the sort of, you know, the world system that we now know. But there were other consequences that were not anticipated, I guess, that leave their mark in the geological record. This is to do with the arrival of Europeans in the Caribbean in 1492 and the subsequent annexing of the Americas. And this led to a huge population replacement, the largest in the last 13,000 years. So, you know, a lot of exchange of people, but a lot of people going over into the Americas from Europe. Okay, so what happened? What consequences were there following this contact with the Americas? Well, you can see that the indigenous population of the Americas was close to 60 million estimate in 1492, and then after European contact, due to a range of factors, but mainly disease, you had a mortality rate of between 80 and 90%. So by 1650, following European arrival in 1492 onwards, you had a massive decimation of the indigenous population of the Americas. So that is a striking graph in itself, but it also set in motion other impacts. Now, the other impacts were changes in carbon dioxide. Okay, so what we have here, this is an ice core record of atmospheric CO2, and we can see it oscillates a little bit, and then we've got a very notable spike downwards around about 1600. So CO2 is being pulled out of the air around about 1600. Now, this is around the time of European contact with the Americas and this 80 to 90% mortality. So we've got disease outbreaks in the Americas. We've also got disease outbreaks in Europe as well. And what's happened is farms were abandoned. So if you've got widespread disease across the world, farms were abandoned, and what were once cleared areas of forest now regrew. So these forest areas, which were starting to grow quite quickly now because the farms were abandoned because people had died, because they were growing on a large scale, they were pulling out CO2 from the air, and this caused a very notable dip in CO2. So this spike represents widespread human death and sort of disease, abandonment of farming, and the drawdown of carbon dioxide. And because it's in the ice core record, it's sort of preserved, so we can use this to mark the start of our current geological epoch, should we so wish. Now, because you've got a drawdown of CO2, this caused climate cooling, and so we also have what's known as a little ice age, which has been linked to this event in part. So this is another leading candidate event. So 1610 to mark the start of our current geological epoch, if it's accepted, to represent global human impact, the establishment of global trade, cross-continental species transfer, modification of the global climate, because we've got the little ice age. Okay, so just to sort of conclude on that and a few reflections on this debate. This is a very live topic. It's not settled. Some people argue for the recognition of the Anthropocene. Others disagree profoundly with it being recognised as a geological time unit. If it is to be recognised, then when did it start? So there's 4 clear candidate events to identify and characterise global scale human impacts, going from around about 7,000 years ago to the most recent being the Great Acceleration from 1940s. But there's a range of issues around this as well, because this is going to define the geological time record, and future generations, and we're talking, you know, thousands of years time, will look back and think, well, how was this new geological time period characterized? Do you want it to be characterized by fallout products from a weapon of mass destruction, which it would be for the Great Acceleration, or colonialism, which it would be with the Orbis Hypothesis? So some of these are quite distasteful as well, and what sort of legacy is that saying to future generations about how we acted? And it's also a novel geological time period. So for the first time in geological history, humanity is at the centre of deciding if we've entered a new geological time period. So again, that is normally done after the fact. We look back and we characterise different geological time periods depending on extinctions and so on. So there's a lot of issues surrounding this, but hopefully for the purpose of this talk, it serves as a vehicle to illustrate that humans have not just had an impact recently or just over the last 200 years, but they've had impacts on climate over thousands of years. It's just ramped up it's just ramped up certainly since the 1940s. Okay, so happy to take any questions that you might have about that.
Many thanks for that, Graham. I'll just check in with Isabel to see if we've got any questions.
Yeah, we have had a couple of questions in. So I think you may well have answered this, but I think it's one that we can reiterate. One of the people watching was working with their class about different kinds of pollution that get laid down into sediments and soils, and they were saying, other than carbon dioxide and methane, are there other compounds that they're using specifically to identify the Anthropocene? As I say, I think you answered that, but it could be a reiteration of those compounds.
That's a great question, because it opens up another part of all this. Right, to recognise a new geological time period, you need what's called a golden spike. So it'll be one record somewhere, and it'll be, you know, a change in chemistry in the sediment or a change in the sort of fossil record, and that is your golden spike, which characterises this event. But you also need they're called auxiliary stratotypes. So you need auxiliary events, so secondary events around the world that point to similar changes in different parts of the world. And so if you're talking about things like pollution, then you might have your golden spike to show human impact, but then you might have auxiliary stratotypes, in other words, other sedimentary records around the world, which show a whole array of sort of pollution. So maybe you've got trace metals in lake sediment somewhere, maybe you've got changes in fossils, such as diatoms, which might suggest changes in nutrient status of different water bodies. So yeah, I mean, you can use geochemistry in all sorts of different sediment deposits to characterize the reach, the sort of global reach of human impact.
Brilliant. And then another question is around the controversy. So why is this proposal of recognising it as a formal geological unit of time controversial?
We are in the Holocene epoch currently, and the Holocene is defined on the basis of human impact and human activity. So during the Holocene, humans started to cut down trees several thousand years ago and continue to do that. And so the Holocene is already recognised to characterise human activity. So to have another epoch to characterise human activity begs the question, does it replace the Holocene or is it added onto it? And so there's all sorts of debates about whether we should retain our current epoch, or whether this Anthropocene should be an epoch or have a lower status. So yeah, there's all sorts of debates about that.
Fabulous, thank you very much. Stacey, I think that's it for now.
Yeah, I think that's all the questions that we've had through today. Just before I conclude, was there anything else, Graham, that you wanted to mention, or are we okay to finish on there?
That's fine. Well, I did put up this last slide. So if you did want to contact me, if you've got any questions that sort of come up that you didn't think of at the time, then please feel free to email me on that address. And there's various social media accounts associated with our departments should you wish to follow us. And then if you're interested in geography, maybe as a degree, then I think that Stacey might put a link in the chat to our departmental web pages. So please have a browse around there, and then get in touch if you're interested in any of our courses.
That's great. Many thanks again to Dr. Graham Wilson for today's Geobites session. We hope you enjoyed the session and you found this useful, and we do look forward to your attendance again at our next event.